Mm. Good morning. Welcome to Krishna's class. Today we shall explore some properties of closed convex sets in the context of a Hilbert space or a inner product space, whatever it is. You can take it as a Hilbert space. Now, before we do that, what is that we are interested in? We will explore through some examples. Okay, so we'll look at the following example. Okay. The problem is this. I will take R2 as an example, our standard model where you can draw pictures. So this is R2 with the usual inner product. So it's a Hilbert space. Now we have a subspace of R2 given. What are the subspaces of R2? The subspaces of R2 are the space itself, the set consisting of the zero vector, and all lines passing through the origin. Now, the non-trivial subspaces are the lines passing through the origin. So, we take one such non-trivial subspace. Let us designate it by F. Now, our problem is this. Suppose you have a vector x. We want to resolve it orthogonally to, or we want to resolve this or as a sum of two vectors which are orthogonal to each other. Okay? So we are trying to work out a scheme for that, and consequentially we can also then write this space R2 as the sum of M and another subspace. Say call it M per orthogonal. That means all the vectors of that space are orthogonal to every vector in M. That's the meaning. So how to locate that subspace? That is one problem. Secondly, what is how to get the resolution of x? So we get the resolution of x and we get the resolution of the space into some of these two spaces. Okay. So what do? We take the coset m plus x. So consider the coset m is a Now we do not consider the other two subspaces at the moment R2 and the 0 itself, because you know that the complementing subspaces would be, if it is R2 then the complementing subspace is the 0 subspace. If it is 0 subspace then the complementing subspace will be R2 itself. So there you get essentially a trivial scenario, but that is not what we are interested in. We want to see it in a non-trivial scenario. So draw a line parallel to M through X. So call this, then you know that this is essentially the set, the coset M plus X. So consider the coset. Now our job is to find a subspace which is orthogonal to M, or how to resolve X into a sum of two vectors one belonging to M and the other orthogonal to it. We try to address this question. So this is the problem. How to resolve now in this context we will recall the following. Suppose in R2 a vector is given. Now this X can be resolved in several ways. Okay. So we can choose, fix one of them and the other one you will have to decide. So how to do that? Suppose Y is such a one of the components. So you want to write this X to be equal to Y plus some Z, where Z belongs to R2. You can actually prove that there is such a resolution once Y is fixed, the resolution is unique and so on. Such things can be. How to work on this? See, it's quite easy to work on this because you know that the vectors add by parallelogram. So you choose, draw this line. It's connecting X with Y, the point X with the point Y. Now you draw a line parallel to this line, okay, and then complete the parallel. So the side, so you have OA, OB, OA and OB are given. Join AB, draw a line OC which is parallel to the line AB. Now this represents a vector in R2. Okay, and call that Z. Now by parallelogram law, X is equal to Y plus Z. Okay, so you don't have, you can always do this. If you fix one vector, the other one can be arranged using parallelogram. Okay, right? So our task here is, given X and a subspace M, you want to choose a vector in M and a vector in R2 such that the property is that these two vectors are orthogonal. So, instead of given x, you want to find out a y belonging to M and a z and a vector z in R2 such that y inner product of y with z is equal to 0. Now, this is the problem. So, how to do this? Simple. See, you take the coset M plus x, that is another line parallel to M, and you want this y to be in M, that is the condition. Okay. So, what to do? Take M plus x, which is a line which is parallel to M. So, what one does is, you can drop a perpendicular from O to this line. Okay, so you call this O A, right? So you have got one vector which is orthogonal to this. Now, how to get the complement vector? The complement vector is obtained by completing this parallelogram. So, this is your A, OA is the vector x, then this is OB, B we fix, this choosing that this is orthogonal to this, and now complete the parallelogram and then decide on C. Then you see that OB and OC, see, OA is equal to OB plus OC. So, in that case, you can right? Call these OCs Y. So, this is equal to Z plus 1, where Z is equal to OB and Y equal to. So, this is the construction that you do. But now the problem is how to draw the perpendicular. How to draw the line perpendicular to M. I mean, you know that such a vector exists, but how do you fix that? It is fixed provided you are able to fix the point C. Now, we can draw OB orthogonal to perpendicular to M if we can fix B on N plus X. Okay, so that's art. In such a way that OB orthogonal. This is the art. So the problem reduces to fix B, satisfying these conditions. So how to fix B? Okay. Now, if you have a ruler and compass or something like that, then you can, in R2, you can actually compute and do it, but then you know that becomes approximated because we have constructional errors and so on. So, that is not the way. So, we have to essentially show that there exists a point in M plus X. So, we have found a strategy in M plus X such that B called B such that OB is perpendicular to M plus X. So, does there exist a point P such that is orthogonal to. So the problem is proving the existence of the point B. If it exists, fine. Okay, so that's what we are after. How to show that such a point exists? Now we will have to go by other properties of B. What are the other properties of? Suppose such a then we see that the distance OB is the shortest distance from O to okay. Why it is so? Because you take any other point, suppose B is there, you take any other point, say B prime, then you compute the length of OB prime. OB prime is actually because OB prime for any point OB prime square equal to OB which implies is less than OB prime and they are equal So can you use this property to identify the point B so that it will be orthogonal? That's the point. Okay, right? Therefore, the question, assume everything goes through smoothly. Then what happens? We have to show that there exists a point B which gives the shortest distance from 0 to m plus x. So shortest from O to so OB gives the shortest distance from 0 to m plus x. Okay, how to find this out? Does there exist such a point? These are all the problems that, okay, at least mathematically, more than actually trying to figure this point, our interest is to show that such a point exists. Thus, there exists such a point. Okay, so what we have is that, because we are trying to generalize this problem, not to exactly this m plus x, but okay, to some set. Okay, what are the properties that m plus x has? Let me look at these properties of m plus x. See, m plus x is a coset, it's not a subspace. In general, it is not a subspace, right? Is contained in R, not a subspace. But a translate of m there's a parallel translate. It's properly contained in R. Now the question that we are asking is, does there exist, what is the point on m plus x designated by B, such a point exists, such that OB is the shortest distance from O to 6. This is the question. Okay. So we feel that it exists. So what are the properties that this has? This line is not a subspace. Okay. That is not a positive property. It's a line parallel to the given line. Okay. So you see that M is a subset of, closed subset of, that's quite easy. So, sorry, M plus x is a closed subset of R. Further, convex subset of R2 in the sense that if U and B are points on M plus x, then the entire line, the line segment joining them. That is Wt, which is equal to 1 minus T PV belongs to M plus X for every the interval 0. So that is the convex. So these are the two properties. Okay, so let us ask now a general. Okay. So we ask a general. Now we ask a general. Suppose S is a subset of R2 which is closed and convex. Okay, suppose it is closed and convex. Does there exist a unique vector in R2? In S. Which is the distance from zero to the now this is the question that you are asking. Okay. So let us explore this. Apparently, yes, we have seen this example. Now we will look at other examples, like you take R2, not only 2 in R2, it's generalized. So take R2. Now let us choose a easy to work out this. Let this be the point 1, 1. Draw a line whose draw a circle with radius half. So this is the circle. That is let S be defined by this is the circle that you. Then from the geometry, see, you are actually seeking. See, suppose your set already includes 0, then 0 itself is such a vector. So we are looking at the case where 0 is not a part of the given set. Okay. So 0 O does not belong to in this case. Okay. Now you see which point has the minimum distance from O. See, it is actually this point. So what are the, see, this lies on the line x1 equal to x2. Okay. Lies on the line x1 equal to x2. So we have to find out the coordinates of that point. And what are the coordinates of that point? See, it is actually this distance. Okay, this distance is root 2 minus root 2 minus. So it is 2 minus half. So we'll work it out. So this is going to be so actually it is y. So you have this is equal to 1 by 4. Okay. So y1 equal to y2. So you want y1 minus 1 whole square therefore y1 should be 1 minus y1 should be 1 minus 2. So y2 which is also equal to 1. Therefore the coordinates of B are and this obviously belongs to S. So any other point in S, for any other point in S, the distance from O to that point is going to be greater than the distance, the length of OB. Okay, for any is greater than the length of this, that is 1 minus root 2, 1 minus 1 by, okay, 1 minus 1 by root 2 is greater than the distance is what? So this is root 2 root 2. This is actually root 2 minus which is equal to distance. So this you can work out. Okay. So that's a geometric fact. Okay. So it appears from examples that this particular. So if this, see the both these conditions are satisfied for this particular set and everything works well. Now we start tampering with these conditions. Okay. Suppose we drop the condition that S is not closed. Given set S is not. So let us take, for example, just define the set. Okay. So S1 you take as is strictly less than That is that means we drop the points on the bound. That clearly there does not exist any point in S1 whose norm is the minimum. Okay, that's quite easy to see. Now it is eventually on this line. So if you take any point here, so it is likely to be anywhere here. It cannot be on the boundary. So you can show that actually for any such point the distance is higher. Okay, and there is no such minimal point that you can identify, because if you pick one of them as a minimal point, you can find another point inside S1 whose length is or whose distance is still smaller. It's quite easy to see this example. So we look at another example. Before I take R1, real line. Now choose the interval 1 to 2. This is the interval 1 to 2. Interval. This is the interval. Or I can, it's better to write this way. The set of all t such that 1, that is the interval 1 to 2. Is the open interval. This is the one that you have. Now you see that does there exist any point in S1 giving the minimal distance? Zero. The answer is no. Because 1 is the point having that property, but 1 is not inside your S1. Okay, 1 gives the minimal distance, but 1 is not in your set. Therefore, you see that dropping the condition that this is a closed set, the expected result may not follow. Okay, so another example is you consider all the rational points in this interval. All the rational points in this interval. That means Q intersection S1. Okay, right? Does there exist such a point? No. So this is enough. This example is enough. Therefore, it appears closeness is an important property. For the validity of such an assertion. We shall keep guessing. Now, what about convexity? Some example where the convexity is not. I'll draw a picture and then show you what happens. So this actually closeness is not that you cannot assert that there exists a point at all. Okay. As a general property, you will have to assume that. See, maybe if you take this set 1 to 2, which is not closed, but still then from 0 you have a, from 0 you have minimal, there is a minimal point. I mean, that may be there, but you cannot say that there exists such a point unless you have this property, because we have produced an example where it would fail. Okay, now let us look at the role of convexity. Okay. Convexity. So let us take an example. Here I draw the picture rather than, see, I define a set or choose a set like this. It may be closed also. Okay. So take S1 as shown in the figure. Now you see that there are 2 points in this set to which the distance is a minimum. Having minimum length. So there are 2 vectors having minimum length. Somewhere here I have, my picture may not be exact, but you get the point. The point is this S1 is not convex. So if S1 is not convex, there may exist minimal point or a vector with minimum norm, but there may be more than one such vectors. So the uniqueness cannot be guaranteed. Okay. See, it is quite possible that, as I said, in this example, for instance, you see that, see this, for instance, you take the case of S1 to be the to be the circle. Okay. So you take S1 as the circle, or let me call this C1 as a circle, C1 defined by equal to now here a unique minimum point exists, although the set C1 is not convex. Okay, so even if it is not convex, you may have this situation, but certainly you cannot make a statement that such a point exists in a general scenario. Okay, therefore this is a pointer to that there may exist such point. Here there are more than one such point that can exist in a given scenario. All these are possible. Okay, therefore we shall speculate that S is a closed convex subset of R2. There exists a unique in S minimum. So this is something that we can speculate. Provided both these properties are there, then you can assert that there exists a vector, the minimum norm, as well as such there is only one and only one vector which is proper. So this is the sort of preliminary analysis through examples to arrive at a result. Okay. Now I have done this for students. For an expert, all this is not required because they can always see these things from their experience. For a student, this is to demonstrate how you compose a conjecture. So this is a conjecture now until you prove it. How you compose a conjecture by investigating examples. Now this is a very, very important step, and this is how mathematics evolves. No theorem just appears or falls from heaven. Okay. Behind that, there is a deep investigation of possibly several examples, and once people get a feeling to the truth of a result, then you write it as a conjecture, and then with established norms of mathematics you try to prove this. Now this is what is happening. So we say this is in R2 that we have stated. Possibly we can state it in a in a in a Hilbert space. So our speculation is this. Now we stretch it further. Possibly, I'm not going to investigate how you prove it on this example and then come to the general theorem. But now I think this introduction is sufficient enough to alert you that one has to analyze good examples before you start proving a theorem. Okay? So because that will give you a much better feel, and possibly you can even work out a proof on this in R2 so that you can generalize it. Yes, but I am not going to do that. I am just going to give the main theorem. So this is the theorem that we are going to do. You know the motivation for doing this. Okay, that I explained in the beginning. I will come back to that after this. So this theorem is going to be a tool in our hands to establish something, and which we have motivated by an example to in the beginning. So let us look at this theorem. Every non-empty closed convex set E in a Hilbert space H contains a unique vector, a unique element of the smallest so this is the statement of it. So look at the conditions. P is a non-empty closed convex set. That's a condition. Then in the Hilbert space there exists a unique vector in E whose norm is the minimum, is the smallest norm for vectors in E. Okay, all other vectors in E has larger length than this. And such an element is uniquely. So let us prove this. I mean, this means the following. Belonging to E. Not only that, x dot is the smallest one. So equality holds. So this is the theorem. This gives the uniqueness. So this is the statement of. Now we shall prove this. It's not difficult to prove this theorem. So we have done most of the investigation. I mean, the students should actually explore a lot of examples to get a feeling for themselves. It's not that you just take the theorem and then write a few lines in the abstract mathematical language establishing it. But it comes out after a lot of thinking behind it and from analyzing a number of examples by various people. Okay? And you arrive at an optimal condition. So here we have shown enough examples to show that you drop either convexity or closeness, the theorem won't. So first part is, suppose such a element exists, we prove this unit. If such an element, if an element is minimum now, this is what we are going to do. Suppose there exist two such elements. Then we show that they are one and the same. Okay, under the conditions of theorem. So we prove it this way. Two such elements. Then we show that it is enough to show that equal to 0. So we prove that norm of x minus y 0. Now here we invoke the parallelogram law. Because H is a Hilbert space, the parallelogram law holds. That's why we did parallelogram law earlier. For x and y, norm of y square. This is in fact true for every x and y belonging. So here, of course, that's a notation. That's a good notation. This we have already proved, so we shall simply use this. Now let delta be the infimum of norm of x down here. Okay. So a vector whose length is given by delta will be the vector serving our purpose. So we want to show that there exists a unique vector having this property. So for first part is uniqueness. So we want to show that there exists a unique vector with length delta. Now you see that this set is bounded below by 0. Okay, by delta. That is what you mean by this. By 0, therefore the infimum maybe in the worst scenario it may be 0. Nothing less than that. Because it is a set of real numbers which is bounded. Therefore this exists. Therefore the infimum exists. Now we shall use this. So by parallelogram law, for any belonging to E, you have 1 by 4. This is the estimate that we want. Want to show that this is in fact equal to 0 under the minimal condition. Now this is equal to 1 by 2 norm of x square 1 by 2 norm of y square minus norm of x plus y by 2 whole square. This is the parallelogram law restated. Whatever we have written here is restated by dividing, taking norm of x minus y and dividing by 4. Pushing the other to the other side and we get this result. Okay. So let me work on this. Since see, this is very x plus y by 2 belongs to E. That is actually 1 by 2x plus 1 by 2y belongs to 1 by 2 plus 1 by 2u. Okay, so this comes from this convexity. Okay, this is true for every this is true. Hence, we have the following norm of whole square is less than or equal to twice norm of y square minus 4 delta square. Why this comes? Because you have norm of delta square, which implies minus we use that in this inequality. Use this inequality. Therefore, you get this. So, if norm of x equal to norm of y equal to delta. Suppose you have two vectors with the same norm delta, which is the minimum value of norm x that you have for vectors in E. Okay, there are two vectors having this. Then we have the following inequality: norm of less than or equal to 0. Why this inequality? See, this will be delta square, this will be delta square, and therefore this is 4 delta square minus 4 delta square, that is 0. So this inequality you are right. And you know that this is necessarily non-negative, which implies. So we have proved the uniqueness. If nx it is unique. So that's the theorem, that's the uniqueness part. But we are yet to prove the existence. So we will prove the existence. From the definition of delta, there exists a sequence belonging to E such that norm of Yn tends to delta infinity. Okay. This is clear because we have defined delta as the infimum of the set of points in E with of the infimum of the set of points. Sorry, the set of points with infimum value equal to. So this is what it is. So there is a sequence Yn because of from that infimum definition, it follows that there exists a sequence Yn such that this is true. Now we will just recall the definition. We have defined delta is defined as the infimum of so this look at this definition. So because of the infimum, there exists such a sequence such that this the limit of this holds. But there is no guarantee at this stage that the limit of this sequence of vectors go over to a vector with delta norm or sorry, go over to a vector x which serves our purpose. Okay, let us prove this. Now, taking x and y as xn and yn, or taking x equal to xn, y equal to yn, ym, we have the following result, that is xn minus or yn minus ym is less than or equal to twice norm of yn square plus twice norm of ym square plus square. So this is from the earlier inequality that we have obtained. Okay, this inequality. Now what one does, as n and m tends to infinity, we then have norm of ym going to 0. That's very easy to see from this inequality, because this goes to 2 delta square. This is 2 delta square minus 4 delta square, that's 0. So this is what you get. So this is less than or equal to 0, which means that this goes to 0. Okay, which implies it's a Cauchy sequence. Now, the condition that H is a Hilbert space is required to show that there exists a limit for yn in H itself. Since it's complete, because H has this property. A pre-Hilbert space may not work. You may have a sequence like this, but that sequence may not converge to an element having the required property, because that's the limit of such a sequence may not be in the space, but may be in the closure of that set. So since H is complete, so the completeness of H now plays a role. There exists an X naught belonging to U, belonging to H, such that now since the closeness of E comes in, since Yn belongs to E and E is closed, this is where the closeness of E is relevant. X naught belongs to E. Now the norm is a continuous function. Therefore, it implies norm of X naught equal to limit n tending to infinity norm of Yn, which is equal to thus if E is a closed non-empty closed convex subset of the Hilbert space H, trivially you need non-emptiness, require closeness, you require convexity, you require the completeness the of the inner product space. Okay, in proving this theorem. Unique. So that completes the proof of the theorem. Okay, so we will conclude today's lecture at this. Now, in the next lecture, we will show how we are going to use it, as I have explored in the beginning of this lecture with an example. Okay, to get an orthogonal resolution. Sorry, not revolution. An orthogonal resolution of a given space. Thank you very much.